Today we're going to take a look at extending our probability knowledge to independent and dependent events. So to start, we're going to take a look at this question here just to get us thinking about what these independent and dependent events are. So a coin is flipped and a card is drawn from a standard deck of 52 cards. Find the probability that a head is flipped and a spade is drawn. So far we've talked about sample space as our strategy for probability. And sample space is important. If we're talking about probability, it's almost always going to be required that we know about our sample space. So we don't want to forget that as we start to do some of these techniques. So let's just see what that might look like. Okay, so a coin is tossed. So we might have a head, might have a tail. And then we draw a card. More specifically, what we're looking for here is a suit. So, I could draw the whole 52 card deck, but what I mean is with a suit there's only 4 things to choose from. So that means the next part of my experiment here, I only need to have 4 branches because I've narrowed it down to suit. So it's just easier for us to draw. Okay, so if I call this heart, diamond, spade, club, heart, diamond, spade, and club, then what this represents is the sample space for all possible events if I flip the coin and draw a card. So for example, I might follow this path. I might get a head and then I might draw a spade. So if we were to take a look, this time we are looking for the probability that a head is flipped and a spade is drawn. So that means I'm going to be taking a look at a head being drawn and a spade. So I can see from the sample space that there is 1 out of 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So the probability is 1/8. Now, how can we shortcut this? Well, if we take a look at what we're actually doing here, there are 2 items in the coin sample space, and there are 4 items in the card sample space. Which branch am I illustrating? Well, the coin represents 1 out of 2 possible outcomes. So this is flipping a coin at 1/2. And then the next part of the experiment is this part here, where I'm looking at a possible 1 outcome in 4. So you might be able to figure out how these can simplify the problem, but we don't need a full sample space. We can just talk about each event, and the product here is going to give us 1/8. So we could have also got this by talking about the coin times the probability of the card, and we would have had 1/8. And then we wouldn't need the sample space diagram. Now, what's important to note here is this is working because we're talking about independent events. So an independent event, it basically means that the 2 events don't affect each other. So when the events don't affect each other, then the probability that both happen is just their product. So again, we'll be taking a look at some of the examples here, and we'll discuss what the difference between the independent and dependent events are, but as they come up it will make more sense to talk about it then. Okay, so let's use the formula now. What's the probability of getting a 5 if I roll the dice 3 times? Well, if I use the formula, there are 3 experiments here, 3 rolls of the dice. Every time I roll the dice, rolling a 6 doesn't affect the next roll. So each roll of the dice doesn't affect the next one, so that way we can say that they are independent. So that's how I know I can multiply them. Then rolling a 5, that's only 1 out of 6 possible outcomes. And I want to do this for all 3. So that means I get 1 out of 216 for the probability. Okay. Now exactly 1/5, that's a different problem. It's it sounds similar, but exactly, we don't want it to be all 3. We just want 1 of them. So if we think about what that could mean, that could mean I roll a 5, a 2, and then a 1, or a 1, 5, 3, or possibly something like a 2, 1, 5. Okay, so the reason I've done it this way is it could be a 5 in the first position, it could be a 5 in the second position, could be a 5 in the third position, but the point is it can't be more than one of those. So let's see how we would put this out in our probability tree. So I want the probability that the first one is a 5, that's 1 out of 6, and then the other two are not. So that's 5 out of 6, 5 out of 6, that it's not a 5, not a 5. Okay. The next thing that could happen is I roll on my first try, it's not a 5, but the second one is a 5, and then the third one is not a 5. Okay. And then finally, I roll again and I end up with no 5, no 5, and a 5 for the last one. So basically I have 3 tries here. I have 1, 2, 3 tries, just like we do over here. Okay. It could be in the first position, second position, or third position. So if we were to put a number to this, it looks like we'd get 25 out of 72. Or in decimal form, it would be 0.347. So about 35%. Okay, so now as we deal with more complicated problems, we're going to talk about a strategy here of using a probability tree. So this is going to be the technique that I usually use, that you'll see me doing in class for us to work on problems. Of all the things I've seen, and I'll mention it where I think there are better techniques, I think the probability tree is easier to put your thoughts and your explanation on paper. So let's take a look at what this question says. The probability that Ashley will pass math this semester is 70%. The probability she will pass English this semester is 90%. Now, this says, assuming these events are independent, what's the probability that she will pass? And then we have a bunch of questions here that we're asking. So if she was going to pass math and English, okay, I mean, it is easy enough just to multiply those two together. But you'll notice there's a lot of questions here about these probabilities. There's a whole bunch of different scenarios. So a probability tree is going to show us all those scenarios. And the way we would do this is we'll say this branch will be that she passes math, and that will be 70%. So that means the alternative is she does not pass math, and it's 30% of the time. Okay, and then the other branches would represent English. So she passes English 90%. She does not pass 10%. So we label the branches like this so we can figure out in the experiment where we're looking for our answer. So if I'm taking a look at the first one, to pass math and English, that means if I follow my experiment, this is where I've headed. Pass math, passed English. So that takes me down here at 0.7 times 0.9. Okay. So that's going to be 63%. Now, if she wants to pass math but not English, okay, then we have a different branch now, so I'm going to clear this. So if she wants to pass math but not English, here's where she ends up, at 0.7 times 0.1. So the probability of that happening is their product, which is 0.07. Okay, now this is where you're going to see the tree starts to get handy, is when we start talking about some of these scenarios. For example, not math, but English. It gets a little wordy here. It's easy to follow it on the diagram. This is the not math branch, and we want to pass English, so it's over here. So that would be 0.3 times 0.9. So that's going to be 0.27, or 27%. Okay. Okay. And clean this up. The next one says neither math nor English, meaning she's failed both subjects. So if she's failed both subjects, that means she's gone down here, which would be 0.3 times 0.1. So it would be a 3% chance that she doesn't pass any of those subjects. Okay, the last one we have to think a little bit more about. So, excuse me. So if she passes only one of the subjects, then what we're talking about is maybe she passes math but not English. The alternative is that she fails math but passes English. So now you can see there's actually two branches here, and again I like the tree because it shows me the two possible paths. This will be 70% and 10%. This one will be 30% and 90%. So going down these branches, it would be 34%. So there's a 34% chance that she passes one and fails the other. Okay, and again, as it shows in the green here, it could be passing math and then failing English, or the other way around. She could also fail math but pass English. Okay, so let's take a look at some more tree diagrams. A ball is randomly selected and is replaced. A second ball is drawn. Find the probability that both were white. Now, this is important. You're going to learn the language a little bit here, but the fact that it's replaced is important because if we were to withdraw that and not replace the ball, it would no longer be independent. Because as I, get rid of one of these balls right now, you can probably see there's a probability here that's 2 out of 3 that it's white. But if I was to remove one of those, I've changed the probability now. Now the probability for getting a white ball is 1 out of 2. So because I've changed the probability, it would not be independent. That's why it's important that we see that word is replaced. So the language will come up more often, and that'll be significant. We'll point it out. But let's draw a tree for this one. So it says we're talking about drawing a white ball or a black ball there. So here's my scenarios. So the probability, if I draw a white ball, is going to be 2 out of 3 for the first branch. Now, let's keep thinking that way. What does this look like now that I've drawn a white ball? Well, now this is what the bin looks like. So when I'm going on to label the next level, there's a 1 in 2 chance that it was white. Oh, I'm sorry, we just said there's replacement. So the ball is replaced back, and white looks like this. So if it's not white, it would be 1/3. So my apologies, I got myself confused on that since I was warning you about it. Okay, we draw it out. There's 1 out of 3 which are not white, and again here there's 2 out of 3 which are white, and 1 out of 3 that are not white. So find the probability that both balls were white. That means we'd have to go down this branch of the tree. So it would be 2/3 times 2/3. So that'll be 4 out of 9, or about 44%. Okay. So we randomly select a bill from pot A in the next example. So that's here. And then one from pot B. What's the probability of getting a $10 bill? What's the probability of getting a $10 bill on only one of those two draws? So again, let's take a look at what our tree might be. Okay, so this is the level that represents pot A, and this is for pot B. So if I wanted to draw a $10 bill, that's the probability that I'm looking at. So let's just call this the probability for a 10. Is equal to, in pot A, it's just 1 out of 3. So the probability that it was not a $10 bill is 2 out of 3. That's these two here. Then in pot B, I can see if I draw a 10, it's going to be 2 out of 4, or half. And if it's not a 10, that's also 2 out of 4, or half. So here's the branches of my tree, so then I can easily answer questions like what's the probability of drawing a 10 for both of them. Okay, so I had to draw a 10 and then draw another 10. So that would be 1/3 times 1/2, which is 1/6. So what's the probability of getting a $10 bill on only one of the draws? Okay, so let's revisit this probability tree. So only one of the draws, that means I can get a 10 from this pot, but then I can't get the 10 in the second pot. Same thing, if I don't get it the first time, then I have to get it the second time. So the probabilities here are 1/3 times 1/2 if I follow this branch, and 2/3 times 1/2 if I follow this branch. Okay, so that'll be 1/6 and 2/6, so that'll be 3 out of 6 or 1/2. Okay, so let's carry on. Why don't you try thinking about how a probability tree might be set up for this next example. And I will mention that maybe possibly you got a little bit of a hint here, but it's not replaced this time. So see if you can set up the probability tree. You pause it here and then we'll take a look together and see if we're on the right track. Okay, so this time when I draw my probability tree, these are not independent. This is a dependent event. So when I look at my probability tree, we have to take this into account. So for a white ball, it would be 2/3, as it's shown here. If it's not white, it would be 1/3, this ball there. So then, if I follow these branches, this one here says that I've removed a white ball. So now let's take a look at the experiment. I've not replaced it. This is what the bin looks like. So a white ball would be 1/2 now, and if it's not white, it's 1 out of 2. Similarly, I have to think about it this way. If I was to draw this non-white or the black ball here on my first try, then that means it's no longer in that bucket. So there isn't actually 2 branches here. I mean, it's okay if we draw it, but white would be 2 out of 2, and not white would be 0 out of 2. It's fine to draw it that way with 2 branches, or you could just draw it as one possibility for white. So it says find the probability that both balls were white. This time, if we follow our way down the tree, both balls are white, takes us to there, which is 2/3 times 1/2, which will be 1/3, or about 33%. So here's, now that we're talking about dependent events, here's the notation that we're going to see. So this is the notation, probability B bar A, and what that means is this is the probability of B given A has occurred. So oftentimes the dependent events are probably more realistic of the real world, right? Like, I mean, what's the probability you bring an umbrella to school? Well, the probability you bring an umbrella given that it's cloudy is probably higher than the probability given that it's sunny. So a lot of times, you know, that's the way we think, is we use some information and that helps influence a decision. Well, in this case, the information is going to influence the experiment. So the way it appears for us on our government exams and our formula sheets is it appears as the probability of A and B occurring is like this, where probability of B bar A is probability of B given that A has occurred. Now, if there's no effect, if A has no effect on B, then this here will just be equal to probability of B. So that's where the formula comes from for the independent events. Okay, so let's try some dependent ones here. And again, I still like the tree model. I think it makes a lot of sense. So let's talk about this here. A factory produces computers that are defective at a rate of 2%. They also manufacture cell phones that are defective at a rate of 3%. If the probability that a cell phone and a computer bought from the factory are defective is 0.0005, let's determine if these events are independent or not. So another thing is, now that we're talking about independent, dependent, sometimes students get this confused with mutually exclusive. So we'll talk about these two, but let's start with independent or dependent. So if they're independent, then that means that A has no effect on B. Then the probability of A and B should be equal to the probability of A times the probability of B. So in this experiment, it tells us that the probability that a phone and a computer are defective is 0.0005, whereas the probability that just a computer is defective is 0.02, and just a cell phone is 0.03. So these two are not equal, therefore they, as you probably would expect, it came from the same factory. There's some connection happening there. These are not independent, they are a dependent event. Okay, so are they independent? No, and this is how we can show it. A must have some effect on B, otherwise those two would be the same. Okay, the mutually exclusive part, what we said we would talk about is, if you remember what being mutually exclusive means, is it means they cannot happen at the same time. So a computer being defective and a cell phone being defective, could those happen at the same time? If they can, then these events are not mutually exclusive. If they can't happen at the same time, they are. So it turns out this is actually a pretty easy one to answer, because it says right here that a cell phone and a computer have a probability of 0.05. So probability of A and B happening is not 0. Therefore, they are not mutually exclusive. Okay, so we'll get back to trying some trees. 2 cards are drawn without replacement from a shuffled 52 card deck. So let's find some probabilities here. Both cards are hearts. You'll see everything up to this point, these all deal with hearts, so it would make sense, why don't we draw a tree that would reflect hearts being drawn. So when I first draw out of the deck, there are 13 of 52. That are hearts, and the non-hearts, let's see here, so it'll be 39 out of 52. So once I've drawn, and here again you're going to get to know this language, it says without replacement. When I think of the next level in my experiment, here I've taken a heart out, so there's one less now in the deck. So now, how many hearts are there? Well, there's only 12 out of 52. How many non-hearts are there? Well, if I drew a heart, that means they're not changed. There's still 39, and there's 51 cards in the deck. So sorry, that there should be a 51. Okay, so one card has come out of the deck, and it was a heart. That's why there are now 12 out of 51 instead of 13 out of 52. For this side of the tree, if I didn't draw a heart, then here the probability that it's a heart is going to be the same as it was before, because we haven't touched them, but there are 51 cards left in the deck. The probability that it's not a heart, this is going to be 38, because I've got one less. And since that card came out of a 52 card deck, there's 51 cards left in the deck. So now I've got all my branches labeled. I can answer questions like, both cards are hearts. So if both cards are hearts, this is where I went. It's going to be 13 out of 52 times 12 out of 51. Neither card is a heart. Well, let's illustrate this branch. So neither card is a heart, then that means I went this way. So it's going to be 39 out of 52. That's terrible. Let me make that a little clearer. 39 out of 52. And 38 out of 51. Okay, exactly one card is a heart. So that means I want, maybe I'll highlight instead, one heart but no heart there. No heart but one heart there. So that's exactly one of them being a heart. And if I look at those branches, that's going to be 13 out of 52 times 39 out of 51. And then on the other branch, it's going to be 39 out of 52 times 13 out of 51. So the last part of the question says both cards are aces. Use the formula. So we'll talk about how the formula can be applied directly without a tree, but you know, in practicality you'd probably do this with the formula because it's only one thing asking you about aces. It made sense to draw the tree out because we used it 3 times. It may not make sense to draw the tree for just one question, but there's no harm in doing it. And again, if you find it difficult to reason with the probabilities, you may want to go and draw the tree for this situation. But if I do this, the probability that I draw an ace, given that the first one was an ace, okay, that's the probability of drawing an ace. So that's, sorry, that should be probability of ace and ace, is the probability that I draw an ace times the probability that I draw an ace given that the previous was an ace. So let's take a look here. What's the probability that I draw an ace from a 52 card deck? Well, there are 4 out of 52 aces in a deck. Now, given that I've already drawn an ace, what is the probability now? Well, there are 3 aces left in a 51 card deck, given that I took an ace out. So, you know, you can see if you can reason that way straight from the formula, it's quicker than drawing the tree. But for some of you, it may be easier to go and draw the full tree. Okay, so the last thing we're going to take a look at here, I'm going to let you go ahead and see if you can work out a tree for this, or if you so choose, you could use the formula. But you may want to pause it here, give yourself a few minutes to try it, and then you can reconfirm your answer with mine. Okay, so a bag contains 5 black marbles. A spinner is divided into 3 equal parts with numbers 1, 3, and 7 labeled on each area. We're going to spin the arrow. Wherever it lands, determine how many red marbles are placed into the bag. So if it landed on a 3, we would place 3. If it landed on a 7, we would place 7. What's the probability that a person chooses a red marble? So again, this is a fairly complicated experiment. You'd want some kind of diagram to help you out. So let's look at the experiment. So first what happens is a spinner is spun, and the probability that it's a 1 is 1 in 3. The probability that it lands on a 3 is also 1 in 3. It says they're divided equally. Probability that it's a 7 is also 1 in 3. Okay, so then let's think about the way the bag is going to look. So again, when you're doing this experiment, you should do them in order. First we spin. Now we can talk about the bag, because we know what's in the bag if we follow the branches of the tree. So if I follow this branch, that means 1 red marble was placed in the bag. So the probability that it's red, okay, 5 black, 1 red, that means there's going to be 1 out of 6. The probability that it's not red, or it's black, I guess in this case, I think, yeah, is 5 out of 6. If I follow the middle branch, then that means I've placed 3 red balls. So there are now 5 marbles plus the 3 that I've just put in. So it will be 3 out of 8. And the black marbles, there are 5 out of 8. And finally, if I have 7, then that means I've gone down this branch, and I'm going to place 7 red marbles in. There was 5 to begin with. So I have a total of 12 marbles now, for which 7 are red. For black, there's still 5 out of 12. So now we're going to follow this down. What's the probability that I choose a red marble? Well, that means I landed on this branch here because I pulled out red, or I landed on this branch, or I landed on this branch. So let's take a look at what those could be. So if I follow that branch, I have 1/3 times 1/6 plus 1/3 times 3/8 plus 1/3 times 7 out of 12. And if we add all this up, we get 0.375, 37.5%, or 3 out of 8. Okay, so that's independent and dependent events, and we're going to start your homework from here.